Thank you for the presentation. Today, I will present to you a study about a recent approach applied in Streparava R&D that concern the integration between structural and process simulation and their correlation with the experimental results. So let's start with a very brief presentation about our research and development department that reflect the structure of our group already presented and can cover the development of both suspension and axle components and powertrain and drive light systems. The process used in our R&D starts from the opportunity to design a component starting from a concept design, for example, from datasheet, going then more in detail with the definition of a product design, that means a design ready for the industrialization. Both these phases are supported by calculation and simulation tools that will be the focus of the presentation of today. And finally, we can prototype the product and finally test them in order to check the reliability of our calculation and validate the product. So now we can see this process used in our R&D applied at the case study that I'm going to present to you. That is an independent from suspension that starts from a concept design. You can see a sketch of the suspension, of the entire suspension. Between the concept phase and the definition of the final design of the component, so before going to the production of the component itself, we have introduced this new approach that integrates some structural simulation with process simulation in order to take into account, also in this preliminary design phase, the effect of the process, and in order so to improve the quality, to lower the cost connected to the industrialization, to reduce the time to market, and to obtain an optimization of the design, also even in this phase. So after that, once fixed the design, we can produce the prototypes that are finally validated. So let's go more in deep with the definition of the virtual analysis conducted during the design phase, starting from multi-body simulation on the entire suspension system in order to find the loads acting on the component that are used during the next finite element analysis that are used to find the stress acting on the component itself. At the same time, some process simulations are conducted for the purposes that I have just explained. And the design took into account the results of both this kind of simulation in order to find an optimal design. Once defined this optimal design, we can proceed with the definition, with the production of the prototypes, with this defined design. And we could make some physical analysis on them, starting from a characterization of the materials, depending on the specific component and the specific application. Could be, for example, microstructural analysis, hardness, and so on. Some mechanical tests, for example, tensile tests on specimen that could be machined out from the component in order to be more reliable in the perspective of the final application, or could be sample separately casted from the component. Finally, once defined these basic properties, we can go on with the final test on a bench test. And we will see in the next slide this kind of test. Another very relevant topic is a numerical correlation between the analytical prediction coming from the structural simulation and the experimental test. This is a very relevant topic, especially for this kind of application for suspension components, and is very important also for new projects, for innovation projects, in order to validate not only the product, but also the project itself. And this is something that we have seen that is really carried out, especially during the durability test of suspension component, of the kind of component that we are developing. So the case study will focus on control arms. Control arms are safety-relevant components, connect the frame with suspension elements and wheels, and usually for heavy application, they are made of steel or iron. The current case study is about an independent front suspension for heavy-duty application, and as you can see in the slide, both the shape and the material of this kind of component for heavy-duty application is very similar of the same component for off-highway application. The material is a ductile cast iron. The shape is an hollow section obtained thanks to the use of lost sand core. So what about the structural resistance? We started with antibody simulation using Adam cars on the full suspension system. The input were loaded at wheels. 3 load sets typical for this application were used, and the output of this first kind of application were the forces acting on the component on the control arm. These forces were used as input of the second kind of simulation that are finalized to find the stress acting on the component on these 3 different load sets. And you can see the results on the picture in the slide. After that, or better, at the same time, we perform some casting simulation on this geometry, both of filling, so the metal, the molten metal that fill the die, and both of solidification, in order to analyze the process and in order to take into account possible defects such as porosities, cracks, or deformations, and in order to improve the design, looking also at the process. So, as introduced, the geometry was continuously iterated, analyzing the results of the process and the structural simulation in order to find optimization of the design, looking at a reduction of weight, a reduction of the defect, and of course, maintaining the same level of mechanical resistance and stiffness. Anyway, there are some defects that couldn't be solved only acting on the geometry. And so it's also important to analyze the process simulation also in this perspective. For example, in the slide we can see that there were some shrinkage porosities that couldn't be solved acting only on the reduction of mass in this area, because it was needed for the structural resistance. And so the same porosity were detected by the X-rays. This means that the simulation were in agreement with what we found on the material characterization. But we could solve this problem acting on a process optimization that was predicted by this kind of simulation. So this kind of simulation is very useful also for this purpose. After that, we proceed with the testing of this control arm that was previously assembled on the entire suspension. And a road simulator testing was carried out with equivalent loads that were calculated after the transformation of the operating forces into time histories, into reduced time histories. The mission performed was typical for this application, was an heavy-duty Latin American mission that lasts 500,000 kilometers and lasts about 500 hours. After, this test was successfully completed. This validated the product, and this highlighted also the careful method of design that we have used because it led to a validation of the component. After that, on the road simulator, we performed the same load set that we have previously simulated with the FEA, and with the same 3 load sets. We introduced some strain gauges in the areas that were analyzed by the results of the simulation in order to finally correlate the results coming from the experimental test and from the analytical prediction. So the correlation were about the stiffness of the full suspension system It was possible thanks to the data of load and wheel displacement that were recorded by the bench sensors and that were used to calculate the entire experimental curve of stiffness. And after that, the second correlation was about the stresses acting on the control arm. The FEA gives the value and the main direction of the stress, and the strain gauges, as you know, gave some microstrains that were transformed in stresses by means of Hooke law. And in particular, the Young modulus were calculated by means of tensile tests on specimens that were machined out from the component in order to be reliable in the perspective of the final application. So here are the first results about the comparison of the stiffness of the full suspension. We can see in black the theoretical curve, and the other two curves are related to the right and left wheels. We can see that they are in agreement. And finally, the comparison about the stresses acting on the control arm. In the bottom left side of the slide, we can see the numerical correlation, that is the novelty of this correlation. For all the free load cases analyzed, the average discrepancy is about 10 megapascal. And we can also say that the FEA guarantees a safety margin because the load predicted by the simulation are always higher than the one registered by the testing. So both these kind of correlations are very important because we can check not only the product and validate the product, but also we can check the reliability of our calculation. This is especially relevant during new project, during innovation project, and for safety relevant components. That means components that are connected to the safety of the passengers and of the drivers. So in conclusion, we see that virtual analysis helped to improve the design, to reduce the industrialization time by an optimization of the design in a preliminary phase, improve the quality of the component, taking into account the requirement of the process analysis and the component characterization. We have seen the case of the X-ray, but there are many other parameters that can be analyzed. And the road simulator was completed, and also the results, the correlation between the prediction and experimental tests were in agreement. And I have already said, but it's very important to underline that this correlation method is a relevant step that closed the loop of our R&D process. So this led us to the conclusion. Thank you for your attention.